My dear Professor, our research is done brought to Wisconsin, Central in Platonic polyhedron.
This is our introduction. First, in triangle ABC, we want to find points S, such as the sum of the distance of segment SA, segment SB, and segment SC is shortest, so we call point S its Fermat point. And second, in a convex polygon with more than 3 vertices, we want to add some points S1, S2, etc. Such as the sum of the distance of vertices to S1, S2. Then we add it is shortest, so we call point S1, S2 is standard point, and the dark blue path is standard tree. This is our purpose. First, find a standard point in a regular polygon. And second, compare the shorter path from mathematical model and the bubble salt film formed on a wire model. Third, find a standard point and a standard tree in Platonic polyhedron. This is our research equipment.
Material and method. In our study, we start from the standard tree of convex hexagon, and then generalize the standard tree of Platonic polyhedron. And now we are going to introduce the planar graph. First one, the standard tree, the Fermat point of triangle. We have two cases. First one is the largest angle is less than 120 degrees, and the second one is the largest angle is not less than 120 degrees. In our study, we only use the first one. And the method is we use segment AB and segment AC to make equilateral triangles, and then connect segment QC and segment BS, which intersect at point P. So point P is the Fermat point of triangle. And then the standard points of square. We choose the parallel sides to make equilateral triangles and circumcircles, and connect segment EF, which intersect at S1 and S2, and they are the standard points of square. And in the other hand, we choose point G as the gravity of square, and then we consider the Fermat point of triangle GAD and triangle GBC, and they are S1, S2. And in rectangle, we choose the shorter side to make equilateral triangle and circumcircles. So S1, S2 are the standard points of rectangle.
Now we'll talk about Platonic polyhedron. This is our topic. Next we'll introduce the standard tree of tetrahedron. There are 4 faces, 4 vertices, and 6 edges in tetrahedron. By former experience, we use in square. We consider about triangle GAB and triangle GCD. We find a standard point is S1, S2, and the red path is standard tree of tetrahedron. Next, we'll check the bubble salt form on model. We made a couple wire model with each side is 10 cm and another one is 20 cm. We put it into bubble water. Pour it upwards vertically and 45 degrees repeatedly. There are only one node inside. Since symmetric properties, we consider a node is gravity of tetrahedron. We found the distance is more than we had in mathematics. We figure out that the bubble salt form is minimum path and minimum energy structure in 2010 American Journal of Physics. We want to find something to explain why the bubble salt form is not minimum path. We'll explore it later.
Now we're going to introduce the standard tree of hexahedron. First, we make a standard tree of square, then move it into the center of hexahedron. Then we consider these 4 rectangles. We find the standard tree of these 4 rectangles and rotate them with an angle. And we found when the 4 rotated angles are equal 15 degrees, the blue edge will match the pink edge. So there are 6 standard points in a hexahedron, and this is the standard tree. In bubble salt experiment, we found there are only 4 nodes in the hexahedron. By calculus, we can find the minimum path, which is larger than the result we found in mathematics.
introduce the standard tree of octahedron. There are 8 faces, 6 vertices, and 12 edges in octahedron. The 12 edges happen to be the edge of 3 squares. Each square has 2 standard points, so we have 6 standard points now. These 6 points just be vertices of a hexagon. After calculation, by inner product, we know that each point connects the adjacent vertices of octahedron is 120 degrees, and this graph is exactly the bubble sort form of octahedron. But by former experience, it should be 2 points less than vertices of octahedron. So there are 4 standard points of octahedron. So we want to remove 2 of them, and there is no cycle. So we remove the paths connected repeatedly, the vertices of octahedron, and remove the paths which cause cycle. Finally, we want to remove 2 points, which symmetrical to the gravity of octahedron, and connected the tree. Now we have the standard tree of octahedron, which has 4 standard points and 9 edges. Then we make a mathematical model and find a shorter path than we had. Then we make a mathematical model and then we prove it in calculus and find the result match our proof. We show the proof on the test.
Now we are going to introduce the standard tree of dodecahedron. There are 12 faces and 20 vertices, and we have 2 methods. Method 1, we consider the hexahedron and dodecahedron, and there are 6 standard points in a hexahedron. And then we divide dodecahedron to 6 same parts and a hexahedron. Then we connect the red edges. So this is the standard tree of method 1. And method 2, we consider 3 golden rectangles. Each rectangle has 6 standard points. So there are 6 standard points, which form an octahedron. And an octahedron has 4 standard points. So there are 10 standard points now. But by our former experience, we know that dodecahedron has 20 vertices, so it should have 18 standard points. So we choose the middle point of red edges. So there are 18 standard points of dodecahedron.
Next, we'll introduce the standard tree of icosahedron. There are 20 faces, 12 vertices, and 30 edges in an icosahedron. The 12 edges is exactly the edge of 3 golden rectangles. Each rectangle has 2 standard points, so we have 6 standard points, which is vertices of octahedron. By former experience, we know that there are 4 standard points in an octahedron, so we have 10 standard points in an icosahedron, and the red path is standard tree of icosahedron. In the same way, we use algebra to make a simulation and find the result match our proof.
Result and discussion. We show our research result on this table and compare with previous results. Tetrahedron and hexahedron are known, and we verify the result. And the previous result of octahedron and dodecahedron are errors. So we revise the result, and we propose the standard tree of icosahedron. And in conclusion, we use mathematical model. We use mathematical software algebra to find the standard points of Platonic polyhedron, and then make simulation. And finally, we prove it from convex n-gun to 3 dimensions. And then we make bubble sort film experiment to compare the model. And in 2 dimensions, the number of vertices of a regular polygon is phi, and the number of center points is s. Then we have a rule s equal phi minus 2. And in 3 dimensions, the number of vertices of a Platonic polyhedron is phi, and the number of center points is s. And if s equal phi minus 2 also holds, then we can prove the minima case we found. And our future prospects. We know the structure of adenovirus is an hexahedron, and the center tree has the minima energy. So if we can destroy the structure, maybe we can kill the viruses. And there are many airports use the structure of polyhedron. And how can we spend less money and have a stable structure? Maybe we can consider our result. And this is our reference. Thanks for listening.